Okay, so we've seen every kind of transformation so far. So what we're worried about now is just putting it all together, tightening up any details. And I think one thing that's important to know is this is like our, oh, you can't see that. Okay, there we go. That's like, so y equals a times x minus h all squared plus k is like our y equals mx plus b. Okay, but that was for linear. It was more simple. This is for quadratics. Okay, but this is like our y equals mx plus b. There's actually three forms. Like same thing with linear, you've got y equals mx plus b, but you've got standard form as well. There are other forms for this. So this one's we call vertex form. Why do you think it's called vertex form? Jaden? Yeah, you get the vertex right there in the equation. Okay, so I get the vertex really easily just from the equation. So we call it vertex form. So if you're ever told to put something in vertex form, you're going to learn how to do that later. And that's what you would do. You're trying to put it in this form, A, H, and K. The other ones don't have that. Okay? It's really useful because the vertex is really important. So this is the best one to use for graphing. If you're ever trying to graph something, this is what you would want. So what you're trying to figure out now is when you look at, let's say, that first equation, what's the A, what's the H, what's the K? Every equation has one. Sometimes they're kind of hiding and sometimes they're right there. We looked at a little application yesterday. We'll look at it again in a moment. That kind of helps you think about that. Okay? So y equals 3x squared has a 3 in it. What does that mean? So this is the one that I was talking about. So there, nope, let's put that back at 0. Nope, sorry, not 0, 1. Okay, so there we go. That's the base parabola, if you can see that y equals x squared. But it has an a value of 1, an h value of 0, and a k value of 0. It's got no shifts and no stretch or compression. But this is what it would look like. So if I move the h, it moves all the points, and you can see that that's what the equation would look like. But it's still got an a value of 1 and a k value of 0. If I move the k value, and then I can also move the a, let's say, up to 2, and that is an example of a quadratic equation with every kind of transformation that you could have, kind of thing. Okay, it's got an a, an h, and a k that are all changed. Okay. So what we're looking at is when you look at a new equation, you're trying to decide where are the transformations? What are they? How are they changing the graph? So always be comparing it back to y equals a times x minus h plus k. So let's take a look at the first one. We're just going to describe the transformations. Can anybody tell me just maybe in their own words even what's going on with that first one? Liam? Yeah, nice. A equals 3. There's no h and there's no k. So this is we call this a vertical stretch by a factor of 3. So this is good. You want to write this down because you want to have a note of this. You can refer back to it. It's a good reference if you're ever wondering about the terminology. Because we do try to get the terminology perfect. We don't make up our own way of saying this. Okay, next one. Again, this one has no shift, no horizontal shift, no vertical shift, but its a value is 1/3. So what does that mean? Alan? It compresses, yeah, very good. So it's a vertical compression by a factor of 3 or by a factor of 1/3. You can say it both ways. Okay, so vertical compression by a factor of 3. And then the last one that we learned yesterday, y equals negative x squared. What does that do? Can anybody describe that? Rip and Preet?
Reflection in the x-axis.
Nice. Reflection in the x-axis. And so it's like a mirror image. If I go back to this guy, I'm going to put everything back to 0. And take this. So there's our, there's our standard curve. And if I make it -1, it looks like a reflection, like a mirrored reflection, right? Like a perfect mirror image of the one that's pointing up, the one that's pointing down. So that's why we call it a reflection. Okay, and so that's the proper terminology for each of those. Just a quick reminder, this is written wrong, but it's supposed to be y equals x minus 2 all squared. What's that one? So again, compare it to our base form, a, h, and k. What is the -2, or what's the 2 in there? Which one of those things is it? Alan, what do you think?
H.
It's h. And h is a horizontal shift. So this is a horizontal shift. What do we have to remember when it's in brackets? Jaden?
It's like the opposite of what you might expect. So it'd be to the right instead of the left.
Right, very good. Horizontal shift right 2. It says -2. You'd think it would go to the left, but it doesn't. It goes to the right. All right. What about this one? Yep. Vertical shift. Yep, this one doesn't do the opposite. Okay, so it's up 5. That's where k equals 5. This one was where h equals 2. Okay, and then a couple where you've got multiple things going on. So again, if I compare it to my vertex form, just the general version, what's happening here? I've got a 2, I've got the x squared, that's fine, and I've got a -1. Perfect. Vertical stretch. Oh boy. Keep going by a factor of 2. And a vertical shift down 1. Yep, where? Okay. Okay, let's see. Vertical stretch by a factor of 2 and a vertical shift down 1. Okay, last one. So no reflection. There's no negative sign out there. No stretch or compression. It's got no A value. So there's just nothing written there. It's like a 1. So there's just nothing written there.
Does it matter which one we put first? Like if we write
No. No. Some people and some textbooks do worry about the order, but for me, no. Really, in the grand scheme of things, order doesn't matter. Okay, so what do we have? Liam.
Horizontal shift to the left.
Nice. Horizontal shift left, and obviously 2. And Alan?
A vertical shift up.
Nice. Vertical shift up 7. Beautiful. Any questions? There's your terminology. We do a lot of this. You do a lot of it again in grade 11 and then in grade 12. There's a little bit. Okay. Everybody good? Questions? Okay, we're going to take a look at example 2. Here we go. Graph each quadratic function, list the important properties of the final form. So you can go ahead and write that out. Oh, you might need a piece of graph paper to do this. So I'll give you a second to get the graph paper out. While you're doing that, you can think about the general version, vertex form, a, h, and k. Look at our example, y equals negative 2 times x plus 5 all squared plus 3. And think about what all the transformations are that are in that equation. Yes, Alan.
If it's a actually it's the opposite. Let's say it's a reflection and then this is plus 3. Would it be plus 3 downwards?
Good question. No, the transformations don't impact each other like that. So a shift up 3 is always a shift up 3.
But then how the reflection went there.
You'll see. So something else that you want to be kind of getting used to and thinking about is, like, we're not, as I said lots of times, we're not using a table of values anymore. So I need to be able to look at this equation and understand some things about it. Not just the transformations, but like more things than that. What is it going to look like? Where is it going to start? Where is it going to go from there? There's things I need to be able to do to this in order to graph it. One of them is we need to be able to get the vertex just looking at the equation. So can anybody tell me what the vertex of that is? Henning? Nice. Because it has a horizontal shift of negative to the left 5 and a vertical shift up 3. So the vertex from 0, 0 is going 5 to the left, which is negative 5, and up 3, which is positive 3. So my vertex is negative 5, negative 3. And then the other thing I need in order to graph is to think about the growth pattern and how that's getting changed. So I know that my regular growth pattern is over 1, up 1, over 2, up 2 squared is 4, and over 3, up 3 squared is 9. That's the standard one. We always start with that. Okay, but for my graph, I have to multiply all of those by negative 2. We saw that yesterday. So I end up going down. Don't say up by a negative. That's really confusing. It doesn't make any sense. So down, 1 times 2 is 2. 4 times 2 is 8. 9 times 2 is 18. I know a lot about this graph. In fact, I can get other things. Like I can get the domain and range, and I can think about the maximum. Like I can think about all those things. I know it has a reflection because it's a negative 2 times everything else, right? So I know a lot about this graph just looking at the equation. That's where you want to be by the time you walk back into class on Monday. Okay, so if I want to graph this, I start with the vertex over 5 to the left, up 3. And if I've been practicing graphing my parabolas, I know that I always go over 1. But in this case, I'm going to go down 2 because I've got a vertical stretch. And I go over both directions. I'm not like recalculating this like in a table of values every time. I'm comparing it to the base version. In fact, I can do that. The base version goes like this. I'll draw it downwards. There's no point in drawing it up because I know it's going to be shifted, and I can draw this parent function downwards. And I'm taking all those points, like this went over 1, down 1, But instead I'm stretching it over 1 down 2, over 2 down 4, over 2 down 8. So I go down 3 and then 5 more. And then from here, I can actually fit this on here. So sometimes you can't fit those last ones, those last 2 points when you stretch it. But I go over 3, down 18. So that's down 3 and then down 15 more. It will probably really help to draw the base function first until it really clicks and you get it and you think you can just draw them. That's why we kind of did that in the learning goal and why we've been doing that every time. It helps to think about how the transformations are impacting the original graph and just getting really good at knowing that parent function really well. Okay, this says list the important properties. Any questions? List the important properties in final form. So that's the red curve up there. So we already did the vertex and the growth pattern. What else is there? There's domain. X is an element of the real numbers. There's range. Y is an element of the real numbers such that, what? Tatum?
Y is smaller or equal to 3.
Good. The axis of symmetry is X equals -5. If you were doing this on a test or something and it said x-intercepts, you would just estimate them. They're not nice, right? Like, so that's -6.1 and maybe -4.9. You just estimate. Don't round to the nearest exact value. Show that it's somewhere in between. We have to say the transformations using proper terminology. So here we go. We got a lot of them. Reflection in the x-axis. Vertical stretch by a factor of 2. Vertical shift up 3, and horizontal shift left 5.
When is it ever the reflection is not in the x-axis?
Oh, good question. In grade 10, never. But it is possible to reflect on anything. So you can reflect on the y-axis, which you'll do in grade 11. And you could reflect on another line as well. Like you could reflect something on the line y equals x plus 4. So that's why we can't just say a reflection, or we can't just say a horizontal reflection or a vertical reflection or something. We say, the way we say it is reflection in the x-axis, but it'll always be like that for us.
Sometimes it's negative, in grade 10, I would just say reflection.
That's right. Exactly. Yep. Jade?
Like, would this question be on like a test?
Yeah.
Like, would it give you, like, say, tell you to do it, or do you have to think about all this stuff in
It will, no, it'll say A, state the transformations using proper terminology. B, like the handout that you have. Yeah. Stretch. It's a stretch. We said that. No, compression. We're going to do a compression next, so you see the change that it makes. Compression compresses it down. Like, not down like those points are going down because it's going negative. It's compared to this graph looks stretched compared to this one. And a compression, the graph will always look compressed compared to the parent function. So we'll see that next. The next one's a compression. Max of 3. So this one has a maximum value, not a minimum value. And I think that's pretty much everything. You could say the y-intercept's not on here, so we can't see it, so we're not worried about that right now. Like I said, the x-intercepts, but... Okay. Any questions? All right, next one. I'm gonna have you do this one with me, and the next one, you probably don't need to copy down, you can just watch. But I think it's worthwhile doing this one with me. Liam.
With the growth pattern,
Yeah.
could you, like, does that mean over one, up one, and then down two? Is that what that means?
So what I did there, you can't see it there? What I did was I thought about the original growth pattern,
Oh, okay.
and then I thought, well, how am I changing that? I'm multiplying by -2, so the negative always makes it go down, and the 2 tells me by how much compared to the original. See how we're always comparing to the parent function? Does that make sense? So I don't go up 1 and then down 2. No, I would go up 1 in a regular parabola. For this parabola, I'm actually going to go down 2 over to down 8. That make sense? Okay, so what's this next guy have? Y equals 1/2 times x minus 7 squared. What does it have? What does it not have? Like, are you starting to see this in that equation? Starting to notice the a value, the h value, the k value? That's where you want to be. So what does it have? What does it not have? Jaden?
Horizontal shift,
Yep.
right, center.
Good. So it's got a horizontal shift. What else? Sarah? It does not have a k. Thank you. Right. So no vertical shift. So what does that mean about our vertex? It's going to be right 7, but not up or down anywhere. So it's still just 0. And then what else is left? The 1/2. So what does that do? That's the a value. It always impacts our growth pattern. So over 1, 2, 3, up 1, 4, 9. But I'm going to take all of those and multiply by 1/2 or 0.5. It's fine to use decimals. And so I go up 0.5. 4 times 1/2 is 2. 9 times 1/2 is 4.5. Yes?
Better to use decimals than fractions.
I think probably because, like, the fraction 9 over 2, how are you going to graph that? Well, you're going to convert it to a decimal and then plot that point, right? So I think it's probably better, but it's really up to you. Like, even if it's a decimal of, like, 0.3333, in this case, you can't graph that. You can't graph 1/3 compared to just 0.3, right? So it's good enough to just be kind of getting an approximation of where that point is. Yes?
Can you also do divided by 2?
Yeah, that's what we did. Yes. Yes. Multiply by 1/2 or divide by 2. Yep, absolutely. Okay, so let's plot our vertex over 7. And it is a bit trickier when you have a compression. Instead of going over 1, up 1, I only go up 1/2. Instead of going, if you want to just watch, it might be helpful. If instead of going over 2 and up 4, I cut that in half and only go 2. Instead of going over 3 and all the way up to 9, I cut that in half, 4.5. What would be my next set of points? If I went over 4, what would the parent function go up? 16. So cut that in half, and we go up to 8. That's not something you have to do. If you fit 7 points on there, that's good enough. But if you can put yourself through that thinking process, you got this, right? Like, if you can just kind of figure out those points as you go, then you understand graphing parabolas. And done. So this has a horizontal shift right 5 and a vertical compression by a factor of 2. It's got one x-intercept at 7. Again, I can't see the y-intercept on there, so oh well. We're going to learn how to calculate x-intercepts and y-intercepts anyway, and then it'll be more important. What else does it have? Axis of symmetry at x equals 7. Minimum value of 0. Do the domain and range as well, like we would do all of that. Alan.
Yeah, that's supposed to be a 7. It says right.
Oh, yeah. I don't know why I said 5. Thank you. Any questions? Yeah. You just keep squaring them. So if I went over 4, square it up 16. If I went over 5, 5 squared is 25. So if you can square those in your head, remember we talked about perfect squares a while ago, and I said these are important to know. There you go. There's another reason why, right? But that's how we get those. That's what you're asking, right? Yeah. You don't have to do that, though. You got to go. Yes. You don't have to do that, but it's good to be able to think through that. Okay, so if you want to just watch this next one, you can sit back and relax, but make sure you're paying attention. Sorry, you weren't done. That's okay. Right.
Are there horizontal compressions?
There are. We just don't do them in grade 10. It would be inside the brackets, like a horizontal shift. Yeah, in front of the x multiplied by the x. And there's another separate little thing to it that we don't need to worry about right now. But yeah, so you see that in grade 11. Yeah. The really interesting thing is like, if you can stretch a graph vertically, but you could also compress it horizontally and do the exact same thing. Like it would look like the exact same graph, right? So how do you tell the difference? Well, you don't. It's not important. It's just making the connection that both are the same.
When are you gonna get the test back?
That is not the question that we need to be talking about right now. Absolutely not.
What are we gonna do with this test?
We're going to have a quiz on this next week.
Monday or?
Probably. Well, let's talk about that after. Okay, so one more. This has a vertex. So we look at this. We look at the values. I got a 3, I got a -1, and I got a -7. Or like a shift to the left one, I mean. So my vertex is -1, -7. And my growth pattern is going to go over 1, 2, 3 up. The base version is 1, 4, 9. But I multiply all those by 3. And I'm going to go up 3, 12, and 27. So it's a big stretch, big distance to go. Here's what I want to show you here. Notice how, like, when you draw a graph, you just have a blank grid like this. You don't have the grid lines already done for you. So I would encourage you, some people take a graph paper and they put like one graph right in the middle of every page. So you do like 12 graphs and it takes up 12 pages of graph paper. You don't have to do that, right? If you think about it a little bit, you could probably fit 4 grids per page at least. So here's what I'm going to do. I know that this graph is going to shift way down. So I'm going to draw my axes in the right place that will accommodate for that. So I'm going to start, like I'm going to plot my vertex way down here. So I'm going to call this -7 and then count up. -6, -5, -4, -3, -2, -1, 0. And that's where I'm going to put my x-axis. And this one has a bit of a horizontal shift, but not much. It's shifting to the left. So I could draw, if I want, my y-axis a little bit to the right to keep it in the middle. This way you don't end up with a graph where like 3/4 of the grid is wasted space because there's nothing in there. Okay, I'm going to kind of maximize my space usage here. So my vertex is -1, -7. Oh, I got to get all my stuff. 1, 2, 3, 4. That's -5. 1, 2, 3, 4, 5. That's x. 1, 2, 3, 4, -5. On a test, you got to include all this stuff. Your test will have blank grids. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And that's my y. So you have to draw in axes with a ruler. You got to have your scale just like this. Okay, so it's worthwhile to practice. So over 1, down 7. And then using my growth pattern, over 1, up 3 on both sides. Over 1, up 12. over 2 up 12, sorry. So I go up 7 and then 5 more. And then on the other side. And then I don't know if I can fit this next one. Over 3 up 27. I can. So up 7 and then up another 20. And then right there. And these ones are particularly hard to draw. So just do your best. Probably won't see too many like that. There you go. So you know where the vertex goes, you know how things change from there, and you should be able to graph just about anything, any parabola. Any questions?